name is Maria Cristina, and I'm a PhD student from University Politehnica of Timișoara in the field of mechanical engineering. My PhD thesis focuses on biomedical applications, and as a matter of fact, in the next minutes I will try to explain to you how to use the ANSYS 2021 program to solve a biomedical application. Meaning, I will try to present to you how to create a three-dimensional simplified geometry of a coronary stent starting from a three-dimensional stent geometry and make a numerical simulation on it. First of all, let's have a short introduction about what these medical devices are. A stent is a tiny mesh tube placed into a hollow structure from your body. For example, this structure can be an artery, a vein, or a ureter. The stents are responsible with maintaining the structure open and with the normal circulation of the fluid within it. What presents interest for us, however, are the coronary stents. These small expandable metallic devices are introduced into the coronary arteries and act like a scaffold to help widen a clogged artery and restore the adequate blood flow to the heart. Coming back to what we want to do, here we have our stent geometry. The relevant dimensions used for this three-dimensional model are adopted from typical anatomical values of coronary artery dimensions, namely an external diameter of 4 mm. Moreover, the stent has a total length of 15 mm and a strut diameter of 0.12 mm. In order to obtain our three-dimensional simplified geometry, we are longitudinally sectioning the 3D model just as we can see here. Therefore, this is a three-dimensional simplified geometry. We are generating it as a helical geometry that respects the characteristics of the 3D model, namely the outer stent diameter, the length of the stent, and the thickness of the strut. Next, I will present to you the steps of a flow solving for a three-dimensional simplified geometry of a stented coronary artery in ANSYS 2021 program. After opening the workbench of the ANSYS program, from the toolbox, we scroll down to the component systems and take Fluid Flow Fluent option and drag and drop it. Once we have it here, we right-click on the geometry and select New Design Modeler Geometry. When we have the Design Modeler opened, we can start creating our geometry. The first step is to select our units to millimeters and our XY plane. Now we go to the sketching mode and from the toolbox we select Line. We draw a line from the origin to the upper part of the plane. We dimension it corresponding to our three-dimensional model, giving a length of 15 mm. This will be our first sketch. The second sketch we create by clicking the New Sketch option. Once we do this, from the sketching toolbox, we select the circle and simply draw a circle on the same plane with the origin. The circle represents the starting point for the mesh wire we will create. We set the diameter to this circle to be 0.12 mm and the distance between the origin and the circle to be 2 mm, which means a diameter of 4 mm. After doing these steps, we select Generate. We want our geometry to generate a flow field as close as possible to the flow from the original 3D domain. As a matter of fact, we will create a helical geometry that is defined by step length and torsion. For this, we click on the Sweep option. We select the profile as our circle, the path as our line, and click Apply. Now we click Generate. We see that we have a red dot here before the sweep options. We click on Edit Selections, click Apply again on the profile, and scroll down to the twist specifications. We select Turns, and for our helical geometry configuration, we will use 4 turns. We click again Generate, and here we have our helical geometry. In order to make the numerical simulation on this geometry, we need to integrate it into a cylinder. This cylinder will represent our artery. For this, we switch the plane to ZX and create a new sketch. Now, we draw a circle starting from the origin and dimension it with a diameter of 4 millimeters, corresponding to our geometry and to the typical value of a coronary artery diameter. We click Generate and then Extrude option. We select our sketch as geometry and the depth to be of 15 millimeters, also corresponding to our geometry. We click Generate and here we have our final geometry. The final thing to do, and the pretty important one, is to go to Modeling, Part, and make sure here in the details of the body we have fluid. Now that we have these things changed, we can go on to the meshing part. Since we don't want our simulation to run too slow, for the meshing part we will select elements with the size of 5 millimeters. Now we go to the quality and from smoothing we select high. We click Generate on our mesh. Once our mesh is ready, we just need to create named selections for each part. For this, we right-click on it, create named selection, and give a name to it. We do this for the inlet, the outlet, the wall, and the wire. After this, we can continue with our numerical simulation. Now that our mesh is done, we can continue with the numerical simulation. We open the setup and we see that here we have already selected the 3D dimension for the geometry, and we also need to click Double Precision. We are ready to start our fluid. Once our solution window is generated, we check our units to be sure that they are meter per square second. After this, we set our time to be transient and our model to be k omega, just as we can see here. Next, we go to Materials, and from the fluid, we create a new fluid that we name blood. We write its properties, meaning the density and the viscosity, and make a mixture with air. Now we can see that here we have both air and blood. From the cell zone conditions, we click on the domain and make sure that our material here is blood. We click Apply and then Close. Moving on to our boundary conditions, we make sure that our stent in is velocity inlet and our stent out will be pressure outlet. For the velocity inlet, we need to read the velocity profile. For this, we go to File, Read, Profile, and select our velocity profile. After this, we go to the boundary conditions, select inlet, and at velocity magnitude, we put our velocity profile. From the reference values, we choose where to compute from. We make sure we have stent in here. After this, we go to Methods and make sure our transient formulation is of second order. We go to Monitors, and at Residuals, we make sure that here we have 10 power minus 7 at all of them. And click OK. Now we are close to starting our calculation. First, we autosave the data file every 10 time steps. We click OK, and after this we go to Initialization. We compute from the inlet, meaning the stent in, and click Initialize. Now we just need to go to Run Calculation and select our number of time steps, our time step size, and our maximum iterations. After this, we click Calculate. This might take a while depending on the geometry and also the computer we run the simulation on. Now that the calculation is done, we can check on the results. What presents the main interest for us are the velocity field, the formation of the recirculation areas, and the wall shear stress. For the velocity field, we will need to create a plane by choosing the XYZ plane, the location, and the plane type. The plane for the velocity field should look just like this. Our velocity field will be represented on the plane. For this, we select a new contour, select our location, meaning the plane, the variable, and click Apply. In order to see our recirculation areas, we will use the streamlines. We create new streamlines, select the domain, meaning all the domains, and click Apply. For the wall shear stress, we will need to create some transversal planes first in the regions that present interest for us. We create them similar to the one that we created for the velocity field. After this, we select a new chart, click OK, select our data series, meaning all the transversal planes that we select from here. The x-axis we select as X, and the y-axis as wall shear. We click Apply, and after this we export all our data. Now we are ready to analyze what we have obtained. We will start with analyzing the velocity field and the recirculation areas. We have chosen the velocity field because it provides us information about the evolution of the flow around the stent struts. The stent placement into the artery produces some side effects to it and to the blood flow. In other words, the protrusion of the stent struts into the flow stream changes the local blood flow patterns, mainly in the vicinity of the wall artery. The regions with the lowest velocity magnitude are associated with the regions where the formation of the recirculation areas take place. The numerical results present one of these areas in the distal part of the strut through this animation. The recirculation flow that we can see here increased the particle near wall residence time in those regions, leading to the development of in-stent stenosis. For analyzing the velocity field, it has been used this velocity profile, where T1 and T5 mark the beginning and the end of the cardiac cycle, T2 and T3 the maximum of the systole and diastole, and T4 the average value of the descending slope of the diastole. Going on to the wall shear stress. This is an important hemodynamic parameter because it shows how the presence of the stent influences the healing of the stented area and the predisposition to adverse effects such as restenosis or in-stent thrombosis. Here we have the wall shear stress evolution in the vicinity of the stent strut and its correlation with the streamlines. From our results, we observe that the wall shear stress is strongly dependent on the strut's geometry. Moreover, the vicinities of the strut are associated with high values of wall shear stress. The normal physiological values for the wall shear stress in a coronary artery are over 0.5 pascals, whereas here we can see that the values of the wall shear stress in the vicinity of the strut are below that. To add more, the values below 0.5 pascals are considered to be critical, being associated with an increased thickness of neointimal hyperplasia. To conclude, this was a brief presentation on how to make a numerical simulation on a three-dimensional simplified geometry of a coronary stent using the ANSYS 2021 program. We hope that this presentation will be useful for bachelor, master, and PhD students, to those working in the field of biomedical applications, and to those who use the ANSYS program in their research activity. For any questions or suggestions, feel free to email us at the following email address. Thank you for your time and for watching this presentation.